Hi guys, welcome to this set of videos. What we're going to do here in this set of videos is now we're going to begin to take a look at some product theorems for line segments inside of circles. And I know that sounds like a bunch of mumbo jumbo. Say what? It'll make a lot more sense as we go through it, but that's essentially what we're going to do. We're going to take line segments in circles and we're going to look at some of the theorems associated with those line segments. Now, there are three kinds of line segments we're going to look at. We're going to look at chords, which we've already talked about. We know what a chord is. And then we're going to take a look at secants. Secants are a new line segment we haven't talked about yet, so we'll first discuss secants and then we'll look at its product theorem, and then we're going to look at tangents, which we just talked about tangents in the last section. So it's a line segment that we're familiar with, but now I told you in the last section we just wanted to think about tangents. We would use it later on to solve problems. Now is where we're going to take those ideas we know about tangents and use it to help us solve some problems. So here we go. In this set of videos, we are going to talk about the relationships. What are the relationships between line segments or segments in a circle? All right, like I said, we're going to talk about three different kinds of segments: chords, secants, and tangents. Now, again, objectives or learning targets, the things that you guys need to be able to do in order to answer our essential question. First, we're going to explore what some of those relationships are of the line segments inside of a circle, and then we're going to use it to solve problems. So we're going to use that geometry. We're going to use those relationships to set up a problem, and then we'll use algebra to solve the problem, right? Just like it has been all year. We learned something about geometry to help us set up a problem, and then to solve the problem, it requires algebra. This is no different. Use geometry, right? Segment relationships to set up a problem. Algebra will solve the problem. So here we go. Like I said, we're going to look at three different kinds of segments: chords, secants, and tangents. And so we're going to look at three different theorems. First, we're going to take a look at the chord product theorem. We've already talked about chords. We know what they are. I'll reintroduce them to you. We'll talk about the theorem. We'll solve some problems. All right, so chords product theorem. Then we're going to look at the secant product theorem. Secant is new. We haven't talked about secant yet, so I'll talk about what a secant line is, and then we'll go ahead and take a look at its product theorem. And then finally, we're going to take a look at what is known as the secant tangent product theorem. Again, we've already talked about tangent lines in the previous section. In addition to that, not only did we talk about tangent, oh, hold up, not my highlighter, pen. Not only did we talk about tangent lines, we also talked about circumscribed angles. So we talked about tangent lines and circumscribed angles in the previous section. Both of these guys right here are going to show up in these two product theorems. Tangent will show up obviously here, the secant tangent product theorem. Both of these guys, both of these product theorems will deal with circumscribed angles, which we introduced you to in the last section. We didn't actually solve any problems with circumscribed angles. We'll do that now here in this section. So, with that in mind, here we go. The first one, the chord product theorem. Here you go. Actually, the theorems are not too terribly difficult. Here's what it says. If you have two chords, they intersect each other inside of a circle, right? So look, I've got two chords. I have this chord right here, chord AB, and I have chord CD, right? I have two chords, they intersect each other at point E. If that's the case, then the product of the lengths of the segments of the chords are equal. Really simple idea. Here's what it says. It actually in the diagram is colored, but your notes are probably printed in black and white. So let me do it for you here so that you can see it in color. I have four segments. I have segment A, E. I have segment E, D. I have segment CE, and I have segment EB. Here's what the theorem says. If I take segment AE and multiply it by EB, so AE times EB. I apologize, that yellow may be a little bit difficult to see, but it's just that segment right there, EB, right? So this chord, AB, gets split into two segments because of that point of intersection. So take the two segments, AE, EB, multiply those segments together. The theorem says that must be equal. It has to be equal to segment CE multiplied by ED. Again, not that terribly tricky an idea, right? You got two chords, the chords intersect each other, it creates four segments. You get four segments. Multiply together the two segments for the one chord. It has to be equal to the product of the two segments for the other chord. That's the theorem. Let me show you how it works when doing some problems. Here we go. Right down here, I have given you diagrams. I want you to find the value of x in each of these. Real quick in this last one, a quick typo. Given this last one down here, if you are given that AD is equal to 12. All right, so that's going to be for this last one. I forgot to give you, you can probably already see there, I didn't tell you what ED was. That's because AD is going to be equal to 12. Anyway, we'll get to that in a second. Let's start with this one. Here we go. Here's what the theorem says. Look at what I've got. I've got two chords. Those chords intersect at E. Set up the theorem. I know that CE, this segment right here, multiplied by ED times ED has to be equal to, here's my other chord, so AE times EB. AE times EB. That's it. That's the theorem. Now, right, that's the geometry. Now it's algebra. Plug in the information you know, solve for the one piece that you don't. Okay, here we go. CE is 6. ED is 2. AE, X, I don't know, that's what I'm solving for, multiplied by EB, which is 3. So 6 times 2 is going to be 12. That'll be equal to 3x. How do I get the x by itself? Divide the 3 to the other side. X has to be equal to 4. That's it, you're done. All right, so really, really simple theorem. This is the chord product theorem. That's the name of the theorem. That's the geometry. Then once you set up the geometry, we solve the rest of the problem doing algebra. All right, so we get x is equal to 4 in this one. Let me put that right here. X is equal to 4. All right, let me erase this so that I have lots of space. I don't want to have to squeeze on you guys here. I did not leave myself a ton of room. Hopefully you can write a little bit smaller on your own notes. On to the next one. Please notice I have two chords. They intersect at G. This one works just like the last one. So what that means is that HG times GJ has to be equal to KG times GI. At this point, it is really, really important for me to point out, it does not matter which order you write these segments in. Multiplication is commutative, meaning order doesn't matter. If you multiply GJ times HG or HG times GJ, you get the exact same answer. Multiplication is commutative. Doesn't matter what order you put these segments in. Doesn't matter. All right, so don't feel like you're going to screw it up if you don't put them in the right order. That's just not going to happen. That's the geometry. Now it's algebra. HG is 9, GJ is 8, KG is 6, and GI is X. So now what we wind up with here then is 72, right? 9 times 8 is 72, is equal to 6X. 72 divided by 6, it is not even, sorry, 72 divided by 6 is 12, and so we wind up with X being 12. Let me write that in here so we don't forget. Again, the geometry is the chord product theorem. From there, just like it has been all year, a little bit of geometry, and then algebra to solve. Geometry, a little bit of geometry to set it up, algebra to solve. Okay, let me erase that again so I'm not squeezing. If my eraser would work. Here's my eraser. Okay, last one. Now, again, like I said, I had to give you, sorry about that little typo, I had to give you this additional piece of information. Given that AD is 12, here's what we know. Here's AD, AD, so the entire length is 12. The entire length is 12. Just this little portion right here, AE, is 3. Now, I don't give you ED, but you can figure it out. We're going to go all the way back to chapter 1, the segment addition postulate. I know that AE plus ED has to equal 12, right? The whole thing is 12, so AE plus ED must be 12. We already know what AE is, it's 3. So how do you find ED? Yeah, subtract 3 from the other side and you get ED is equal to 9. Fantastic. So I know that this guy right here is 9. Now we're all set. We'll go ahead and set up our chord product theorem and solve for my other unknown, in this case, x. So I know that AE times ED has to be equal to CE times EB, right? So I take my my 4 segments, AE, ED, multiply them together. Then take CE and EB, multiply them together. The theorem says they have to be equal. That's the geometry. At this point, guys, plug and chug. Let's see what we get. 3 times 7, sorry, 7, geez. 3 times 9, my bad, is equal to x times 14. Okay, great. Well, 3 times 9 is 27, so we get 27 is equal to 14x. Divide both sides by 14. Okay, so 27 is not evenly divisible by 14. That's okay. You're going to get a decimal. I get 1.93, and that's good enough. That gives me the value of x, which was 1.93. Alright guys, that's the way the theorem works, the chord product theorem. Not too terribly tricky an idea, doing problems just like we've done all year, right? This is the geometry. The theorem is the geometry. Once you apply the theorem, then it's algebra from there to solve, right? Using the information you've been given to solve for the one thing that you don't know. Head on over to the next page of notes. We'll take a look at the secant product theorem. I'll meet you guys there.